So 4, 2, 0, 1, 2, 3, 4, 5, 6, 7. This is 5. So now I've got how many bins? This is bin 1, bin 2, bin 3, bin 4, bin 5. So far I have 4 balls, 2 balls, 6, plus 7, 13, plus 5, I have 18, 1 and 1. So the essential part here is to recognize that the way to throw those balls into bins, it's effectively the ways of cutting a string of 20 circles with 6 separators. So this is 20 circles, which are bins, and 6 separators, separator bars, which are the number of, these are balls, number of bins minus 1. And then if I put it this way, it should be easy to see that this is nothing else than number of balls plus the number of bins minus 1. This is the separators. Choose number of bins minus 1. Please, when you write this, write it that way. This in our case will be 20 plus 7 minus 1. Choose 7 minus 1 in this example. Don't write it as 26, choose 6. Write it as 20 plus 7 minus 1, choose 7 minus 1. So be clear which ones are the balls and which ones are the bins. Now there's a variation of this, which we did. What is the number of ways with the constraint every bin has to have at least 2 balls? And we did this, I think, a recitation, this variation. We can do exactly this, but before doing it, we have to put 2 balls into every bin. So place 2 balls in each bin to satisfy that requirement. And now the rest is still a balls into bins problem, but with how many balls? If I place 2 balls in each bin, the remaining balls is what? The initial ones, which are 20, minus 7 bins times 2. How much is it? 6. So now I have 6 balls into still 7 bins. This answer to this question, according to my strategy here, it's still 6 plus 7 minus 1, 7 minus 1. Same thing. I just replace the number of balls. Instead of 20, now I have 6. And do I have any options for doing this? Is there any, when I say place 2 balls into bins, each bin, is there many ways to do that? Is there only one way to do that? It's only one way, because balls don't have ID. So this is identical balls. And this is distinguishable. So bins have IDs in here. Because there was no really a choice for me in here, I didn't have many options. It's only this number that counts the number of ways. And I think there was a variation in the online homework I've seen last night. What if bin, a particular bin, bin 4, has to have at most 5 balls? Then what? So this constraint in here is every bin must have, this is at least. At most means bin 4 in particular has to have at most 5. So there's a variation with oranges and apples and a fruit bowl or something like that in the online homework that asks this question. Not hard. This you can, I can leave this as exercise. You can, this easily could be a quiz question next week. You know, have balls into bins, there's apple and oranges, and you want at least or at most that many. There's another variation which is difficult, beyond this class difficult, where it says not just bin 4 has to have at most 5 balls, but all bins at most, say 5, or a general K. Then what? How many ways can I put those balls into bins such that not a particular bin has at most 5, but all bins have at most 5? Is this the converse of this when I say every bin has at least 2 balls? What's the converse of this statement? When is this not true? If I say this is a particular number of ways to put balls into bins, such that every bin has at least 2 balls. If I say that's not the case, what am I saying? At most or at least? At least one bin has less than 2 balls. Is that this statement? No. At least one bin, it's more close to this. It's not the same. This is exactly bin 4, but the converse of this would be at least one bin has 0 or 1 balls. That's the negation of saying all bins have at least 2 balls, right? Hands up who's with me. Now, that's close to this if I negate this statement, but not to this, because when I negate every bin, I don't get back all bins. When I negate every bins have something, the negation of that is one bin has something else. So this is a more difficult statement to prove, but it's doable, just we need more math to do so. We're not going to do this. So that's a recap. And there's a bunch of other problems that are being recapped and discussed. We did some of them. I think I'm going to make a list with all these problems. And I'm also going to post today the recitation answers for the first 3 recitations. That is, if you start for the quiz, you should focus on the simple problems. Okay, in this class, being honest, we say, here's all the simple stuff. Occasionally, we say, here's a not so simple thing. The not so simple things cannot be part of your quiz. So if you focus this weekend and the early next week on the quizzes, you should definitely check your recitation paper against the answers. Now, you won't have those until the quiz, but you can still check. I'm going to post the answers online. You go through those to see if they make sense. It should be a very quick process there, because those things are quickies. Doesn't take a long time to go through that. So now, one of the problems that I want to talk about is something that we left last time. If I have a table here, lattice grid, and I'm going from here, say this is a 5 by 5, 1, 2, 3, 4, 5, 6, maybe more. So 1, 2, 3, 4, 5, 6, 7. And this is 1, 2, 3, 4, 5, 6, 7. So that's a square grid, right? Last time we said this, in how many ways can I go from 0, 0 to, so I'm starting here, this is the start at 0, 0, and I want to end up here at 7, 7. So I'm looking for paths from 0, 0 to 7, 7, where the path can only go right or up. So that's allowed. So in here, obviously I have multiple possibilities. I can go, for example, right, right, up, up, right, up, up, right, right, up, 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 right, right. But obviously that's not the only way to go. I can go in many, many ways. And I think somebody at the very end of the lecture on Tuesday solved this problem. how many paths I have there. This is not a hard problem. How many total moves are required?
16.
How many? 14. Let's just call this n in general. The example is for n equals 7. But in general, I have n by n squared. Could be 7, could be 9, could be 15. In general, the total number of moves have to be how many? 2n, right? Because I have to move n to the right and n up, since I can't go back and I cannot go down. Okay? I know out of these moves, n have to be up and n have to be to the right. I don't know the order, because I could go right, up, right, so on and so forth. Thank you. So I don't know the order, but I know there's 14 and half of them, 7 will be right, 7 will be up. So in how many ways can I do this? How many different ways? By different ways, I mean even a slight change in the path counts as different. Even though two paths might have a lot of edges in common, if they have a little difference, it counts as different paths. So the way I can imagine writing a path is to have 2n spots. Those are the moves. And to put here which one goes up and which one goes to the right, right? Any sequence like this, right, up, right, up, right, so on and so forth, right? It's equivalent to a path. A sequence like this, which moves is right and which moves is up, tells me how to go. Go first to the right, then to the right, then go up again, then to the right, so on and so forth, right? Every path can be converted into a sequence of moves. Is it true the other way? Every sequence of move is a valid path. Anywhere I draw a bunch of rights and ups with a condition that exactly n are up and exactly n are right. Is that corresponding to a path? Anywhere I put those, can I put up, right?
Yeah.
Can I put right, up?
Yes.
So anywhere I put those things, as long as n and n, there is a path for that. So because there's a one-to-one map between the paths and those sequences, it comes down to how many ways I can put a sequence of n moves up and n moves to the right out of 2n spots. How many ways is that? What the choice comes down to?
14, choose 7.
Right. Let's say 2n, choose n. I think he means you have 2n spots and you just have to choose which n of them are the one to the right. Because the other n will be the one that go up. Or you can say the other way, which n of them I choose to go up, the remaining n will go to the right. Right? So in my case, in this example, it would be 14 by 7. But I could have drawn this grid to be 9 by 9. And this would be 18 by 9 in that case. Great. I think we've done this last time. I think everybody was happy with it. I don't think it's a hard problem. This is literally a quiz question, more or less. Now, what I want to do here is to not count all the paths. I'm interested in a particular, it's a blue marker. That's good. And the red one is probably not working. At least the red one is working. Good. So here's what I want to do now. That's all good. I want to declare some paths are legal if they don't cross diagonal. But they can touch. So touching is allowed. Crossing on the other side is not allowed. So where is the diagonal? Obviously it's from 0, 0, right? The diagonal is this line. That's the diagonal. Is it clear? This is the diagonal here. Now, I mean they don't cross, let's say crossing up. It doesn't matter which way, this problem is symmetrical. I could say all the paths on the upside are legal and the downside is illegal. Or I can say the downside part here is legal and the up is illegal, because this problem is perfectly symmetric. It doesn't matter which one is legal, which one is not. Now this path, let's say up is, don't cross up diagonal, so this is the illegal part. And this is the legal part. This path is not legal because it crosses up, right? So what would be a path that would be legal? Let's say this one here goes this way, right? And now it goes right, up, up. Can I go up to this point?
Yes.
Yes. But then I have to go to the right, because if I'm here, if I go up, I'm crossing the diagonal, right? If I go here, and here, and here, here, here. So now this path in here, that's legal. So I want to count how many paths are legal. Obviously, this is a smaller number than that, right? These are all the paths, correct? The number of legal paths now, it's got to be a subset of those, because every legal path is a path, so I'm expecting a lower number. What do you think? Can I say half? Makes sense to say, okay, out of all these paths, half of them are legal, because it looks like diagonal is exactly chopping this thing in half, so I'm just throwing as half of them are legal, half of them are illegal. Would that be right? Yes.
It doesn't work because if the bottom right part that had all the paths was at, and the top left was also at, we couldn't have that because there's also one crossover, so they can't go.
So he has a very good argument why my answer is wrong. Why is it that the number of legal paths is not half of this? Here's his argument said properly. His thinking was right, just the way he said it is a little funky. He's saying take all these paths, all 2 to the n total paths. And he split this quantity into 3 disjoint cases. Here's the cases that he said. He said number of paths legal, I'm going to put here legal down. That's what they say, legal down. Meaning the ones that the whole path have to be in the lower side of this matrix. That's what legal means, right? It can touch the diagonal, but if you look at every edge of the path, the edge have to be below the diagonal. To that he says, for every path that you think legals down, there is one legal up. What the legal up means? The whole path lives above the diagonal, right? So there's a number of legal paths up. And now his argument is that this is not the only paths that there are. If those would be the only paths, since this has a one-to-one correspondence to that, it'll be indeed what I said. Take the total, divide by 2. But his argument is that there's some other paths. There's some number of paths kind of that go up and down. Like the first one I draw. See, the first one I draw here, it's up the diagonal, and then it's clearly below the diagonal. This path is neither legal up nor legal down, because it moves up and down. So because of this number of paths, clearly those two quantities cannot be half of the total. If this would be half of the total, and this would be another half of the total, which they must be the same number, right? That's your argument, because this is a symmetric problem. Then you wouldn't have any paths that go up and down, but you clearly do have paths that go up and down. So that can be half. Very good. So now, how do we count them?
For each right arrow that movement we go to the right, there is a corresponding amount of movements that you can make up. So we could split it into almost a ball into bins kind of thing. And for each movement you do to the right, you can add like an ability to move up. So like for if you have like a graph of 3, the first thing would only have one possibility, the second would have 2.
So
So,
let's
like, it
just
would-
write that down. Let's see if I understand it. The first.
Actually, I think it's more like an n plus n minus 1 all the way down to 1.
M, who's
n,
M?
n being the total amount of movements to the right.
So that's n. We know this n moves to the right and n moves up, total. They gotta be. That's true for all these paths. All these paths, legal down, legal up, and legal right, they all have n moves to the right and n moves up. This one has n moves to the right and n moves up. All of them have n moves to the right and n moves up, right? Because to get from there to there, I have to move n this way and n that way. So your argument is this is n plus.
N minus 1, n minus 2, so
I
on
keep
and
adding
so
here?
forth until 1.
Plus like that.
Yeah.
So this is plus 2 plus 1.
Yeah.
This is the number of paths.
Yes.
I don't think that's true. But this is good. This is how you have to attack a hard problem. You have to try out things. I mean, the worst thing you can do is to not try anything, okay? So trying out things, but then why is this not the number of paths? You know, I know for sure it's not. Yes.
I didn't have an answer to that, but it's just like that's not the number of choices you have each time. Like you go down.
Plus, there is an addition between those choices, right? If those would be choices in the sense of this, how many choices I have the first round, this how many choices I have the second round, what would this be? If this would be choices that I can make a choice here, and for each choice I can make a choice the second round, and for each choice I make a choice the third round. This sounds like what? It's not like a product rule, right? Every time you make a choice, and based on that you have n minus 1 choices, and based on that you have another number of choices. That's clearly a product, not a sum. Sums in combinatorics come from the sum rule. To get a sum in the end on a count, you must have split into disjoint cases somehow. This is all the paths red, and this is all the paths blue, and there is no path that's red and blue, therefore I'm counting those and sum it up. So as a grader, when I see a sum, I'm looking for the cases immediately. Where these sums come from, these counts. What did you count here, that disjoint sets? So if there's choices that are consecutive choices, it sounds more like a product. But the answer is neither the sum nor the product. It's not n factorial, the number we're looking for. So this is a difficult problem, okay? This is not one of the things that could be done easy peasy with what we have. So let's see how far we can go today. And unfortunately, I can't go until the end of the lecture because there's stuff on the way that we need to do, like high school stuff that you might have forgot. So I have to do that too at the end. So I can't push it all the way to 3:15, but let's see how far we can go with it. And at some point, like remember 2 weeks ago, that Hamiltonian path? At some point, some of you may disconnect, may say, okay, this guy is exaggerating here. If you feel like that, that's perfectly fine. You can disconnect from this thing. Friday afternoon, who wants to deal with Catalan numbers? The answer is Catalan number. It's a very famous number in combinatorics. And there are about 300 problems that have the same answer, Catalan number. This is one of them. So before we get into Catalan numbers and how they work, and we'll try to provide an answer to this question, okay? May not be a complete proof, but we'll get an answer. I want to show you other problems that have the same answer as the Catalan number. So the number of legal paths here, by legal I mean legal down, it's the same as other problems. So I'm going to show you some of these problems. Here's one such problem. I'm going to start with one of that's my favorites. Again, there's about 300 combinatorial problems that relate to Catalan number. If you do any serious combinatorics of number theory, you would have to get to Catalan numbers pretty quick. Like, there's no way to avoid them. So, ways to put n pairs of parentheses legal? So in any algebraic expression or programming expression, when you put parentheses, what does legal mean? So for example, this is legal here. 3 pairs, so I'm going to say here n equal 3 for this example. Here's 3 pairs. Is this legal parenthesization? What does legal mean for parentheses?
Means you open the parenthesis before you close it.
Right. I can't have open 2 and close 3. Right? In any expression, whether you do algebra or you do programming or just any algebraic expression with parentheses, doesn't have to be numbers. You can't open a certain number of parentheses and close more than what you open. You can open more than you close, but not the other way. So what are the legal options for 3 sets of parentheses? Could I do this? Is this legal? Can I do this? Is this legal? By open and close is not just at the end, right? At the end, I'm always going to have 2 n total parentheses, n open and n close. It's not just at the end. Legal means at any point, the number of parentheses, I'm putting here number of open parentheses, how does it have to be versus the number of closed parentheses?
Greater than or equal to?
Greater than or equal to. The DS sign is the number of. So that's not just at the end. At the end, they're always equal, right? The n open and n closed. But anywhere you look, I look here, how many open, how many closed? Up to this point. 2 and 2. How about up to this point right here? 1, right? If you look at those expressions, everywhere you have more open or equal than closed. So what is another way to put parentheses? Can I do it this way? And there's one more that's legal. I say this is the only ways, 5 ways, to put open and close 3 sets of parentheses. Of course, there'll be more ways if I have 4 sets of parentheses, and more ways if I have 5 ways. But this is the only legal ways to put 3 sets of parentheses. So I say this problem, from a counting perspective, is the same as this problem. There is a one-to-one correspondence between parentheses and paths. But this, of course, is a way too big lattice for this problem. What would be the lattice that would correspond to this problem? It would be a little smaller, right? What lattice do I need to make the paths in this lattice? Every legal path will correspond to a way to put parentheses. How much this lattice should be? 3 by 3? So if I have a lattice 3 by 3, and I'm asking the same exact question, you want to go from here to here, right? This is 3, 3. This is 0, 0. What's a legal path again? Cannot cross the diagonal up, so here's a legal path. What is this path? Up, right, right, up, right, up. This particular path corresponds to which sequence of parentheses? Yes. Which one? This one? She's saying this path that I just draw here corresponds to this one. So I'm going to maybe circle this one like this, and maybe I use this marker here. Let's draw another legal path. Can I go up initially? No. So I have to go right. Maybe I go up now. I go right, right, up, and up. Now this red path, is it legal? Which parenthesis that corresponds to? Which sets of parentheses? The second one? Do we see that there is a one-to-one correspondence between how you put parentheses and the legal paths? The reason this is very easy to see is because they have the same exact constraint. In this side, I can't move more at any point in the path because I didn't cross the diagonal, means I move to the right at least that many times as I moved up, which is to say, how do we build the one-to-one correspondences? The open parentheses correspond to,
Right.
moves to the right. So the open parentheses corresponds to the move to the right, right? Equivalent. And the close parentheses corresponds to the move up. So there's a very mechanical analogy here that says number of open parentheses has to be at least the number of close parentheses. In this way, we say number of right moves has to be at least the number of up moves anywhere in the path. How about the total length? What's the total length of this string? How many symbols are here? 2n, right? It's 2n length. How about the length of the path? 2n. So I think everybody can see this is a one-to-one analogy. If you can count paths, you can count parentheses, or the other way. If you count parentheses, legal parentheses, you count paths. But that's not to say the problem's easy. Like counting parentheses is not that easy.
If there has to be a one-to-one correspondence, how come in the definition you put greater than or equal to and not just equal to?
Greater than or equal at any point. I think you're looking at the end. At the end, they always equal. It's n to the right and n up. But if I go to this point here, up to this point, I have 2 open and 1 close. So they're not always equal. They equal sometimes, like here equal, there's 2 and 2 up to here, right? If I look at just this beginning of the path, open, open, close, close, I get 2 and 2. But if I look open, open, close, open, what's the score up to here?
It's 3 open, 1
3
closed.
open, 1 close, right? So it doesn't have to be equal all the time. It's just equal sometimes, and in the other cases, opens is bigger. Just like the same with the paths, right? When is this path reaching an equal point? When it touches the diagonal. Every time this path touches the diagonal means the open parenthesis or the right moves is equal to the close parenthesis or the up moves. Every once in a while it may touch the diagonal. But when it doesn't touch the diagonal, the right moves are more than the up moves. Similar parentheses. Hands up, who's with me? Good. I'm not going to solve this problem because I don't know how to solve it. It's equally difficult. I'm going to just put another problem. That's similar to the parentheses, but not the same problem. It says, here's another problem. Order, let me write it here. Here, actually. Order of multiplying n plus 1. In my case, n plus 1 is what? If n is 3, n plus 1 is 4. But this is just an example. 3 and 4 is an example. This stuff works for any n. So how can I multiply order of multiplication? I mean what? I could do a times b first. So the values are a, b, c, d. We're not concerned with what the values are here, just the order of multiplication. They could be matrices, for example. Multiplication in most mathematics is a associative property, right? If I have a times b times c, I can do ab first, and the result I multiply with c. Or I can do bc first, and the result I multiply with a, right? Can I do that with matrices? Yeah. A, B, C. I can do it this way, or I can do it this way. I get the same result, right? Certainly I can do it with numbers, right? So typically in most groups, algebraic structures, multiplicativity is an associate property. It's addition too. You can add up the first two and then the third one, or you can add the last two and then the last one. You get the same value, right? So we know we're getting the same value, but the order of the multiplication, there are several orders to do it. So here's one order, AB, then I multiply with C, then I multiply with D. Now, those parentheses are not those parentheses. These parentheses are put here just to indicate the order of multiplication. So what's the first multiplication here? B. Then the result times C, then the result times D. So I don't want you to think those parentheses are those parentheses. I want you to think of that's the way we typically in algebra put an order on multiplication to know which ones go first. What else can I do? Can I do A times B, then separately C times D, and then make the product between them? Can I do A times B times C? So B times C goes first, multiplies with A, the second multiplication, and then with D, the last multiplication. What else can I do? I can do A, B times C, and then, so these are not the same, right? What's the order here in this one? B times C goes first, then multiply by D, and then multiply by A. In here, B times C goes first, then multiply by A, and then by D. And there's one more that is A times B times C times D. In this case, CD goes first, then the result is B multiplied with that, and then the result is A multiplied with that. Now, this is not a trivial problem. You could think, who cares, right? I have 4 numbers, I can multiply in whatever way. That's true for numbers, but it's not true for matrices. While we're getting the same result for matrices, the order in which you do the multiplication affects very dramatically the computation time. If you do it in one order, it could be very fast, and in a different order, it could be very slow. You will see that a little bit later, why that is, the way the matrices are multiplying in a certain way. Now, notice that I have 5 ways to put parentheses. We already know it's a one-to-one correspondence. There's 5 ways to put legal paths. Is there any other way to multiply 4 values? Will I put every possibilities in here, or I miss some? Associative is not commutative. I can't change the order. So I can choose which ones to multiply, but the order has to be this way. So I think I put all of them here, which is also 5. And I'm saying there is a one-to-one mapping between those parentheses and these multiplications. But that mapping, even though the parentheses are on the board, that mapping is not obvious, right? Why there is a one-to-one mapping here? Which is true. There is a map. Yes.
Because you're using the same number of parentheses.
Right, and that's what I thought, to be honest. When I read about Catalan number, the first time I said, that's got to be obvious, right? I mean, how many open and closed parentheses are on this side? 3 and 3, right? And that's got to correspond to 3 and 3. Like in any way you put parentheses, you get a order of multiplication. But when I look at them, it's not true. Like look at this 1, 2, 3. If I eliminate the A, B, C, D here, I just look at the parentheses. This is not that, right? Right, but can you describe this one-to-one map in exact terms? I agree what he's saying. You have 3 sets and 3 sets, but why is it that for any way you put the parentheses, you get the multiplication order? Or more specifically, which order is that? If I just give you one corresponds to who? That's not clear to me. How do you make that correspondence? I agree that there's 3 and 3, but what's the correspondence? So I spent some time trying to figure out the rule. I came up with something. I don't think is the most obvious one, but that's the one I have, so that's the one I'm going to say. You know what I come up with? I say, if you want to transform this into that, remove, what is it? Remove all the letters in here. Let me make sure I get this right. Yeah, here's the one-to-one map. From left to right. Remove letters, and you're going to love this one. Remove open parentheses. These ones that you think we like, we're actually going to get rid of them. Okay? And then I keep what? If I remove the letters and the open parentheses, what's left in here? And there's something else left. There's a multiplication dot, right? So I'm gonna close, I'm gonna keep the close parentheses, no change. And I'm gonna, remaining the multiplication dots, I'm gonna make them open parentheses. Sorry. When I prepared the lecture 2 years ago, that's the best idea I had. I knew there is a map, and I couldn't come up with something better. Maybe you can. Let's see, does that work? What happens if I remove and replace the dots with open parentheses? What this guy becomes? Open, close, open, close, open, close. Is that this one here? How about this one here? What this one becomes? Open, again, I'm ignoring the open parentheses, I removed those. So get open, open from the other dot, close, close, open, close. Is that this one here? So that way I think they map really nice. This one to there, this one to here, this one to here, and this one to here, right? How about this one here? If I remove the letters, so I get dot, open, dot, open, dot. Sorry. Hey, I got lost. There's a missing parenthesis here?
Yes.
So dot, 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 close, close, close. When I do this mapping, do I get this one? So that's the one I came up with, yes.
What if you rearrange the order, like the way you multiply for example, what if like if you rearrange this so that you didn't have to remove the open parentheses, you could just remove the multiplication dots?
You mean rearrange, permute B and C?
No, rearrange like the order, the different orders. So like say flip the top one, flip the bottom.
Right, move this one there and that one there.
Yeah.
You're saying they could probably another map that works.
Yeah.
Like the different map. I agree. That's how I felt. But then I tried for half an hour to find one, and this is the best I could come up with. I'm sure there's another map because there's 5 objects here, 5 objects here. If what he's saying, maybe this one can go here, and this one there, and this one there. But when you create a one-to-one map, you have to specify the map or the procedure. How is it that you take this and you end up in there? So I totally agree. There's probably other maps that work in here. The only one I could find easily is this one. Actually, it was not so easy. And can I go the other way? Is that answering the question? I think you can find other maps, perhaps by not removing parentheses and try to do a procedure with them. How do I go from here to there? It to be a one-to-one map, I have to be able to go both ways. If somebody gives me this, how do I make it into that? Can I kind of reverse this map? So the open parentheses will become multiplication dots. And if I have multiplication dots, dot, dot, close, close, dot, close, will that be enough to determine the order of multiplication? No. Can I, from here, build this expression? I think I can. Like if somebody tells me, where are you going to put parentheses, so these are your multiplications dots, I know it's A, B, C, D, so after the last dot, who must be here?
D.
D. After this dot, who must be here?
C.
And then in here is? And then here is A. So now, where do I put parentheses to be legal? Remember, the number of open cannot be smaller than the number of close. So if this guy closes 2, what needs to happen here? I have to have open, right? And then where is the other open? Where can the other open be for the dots to act correctly? Has to be here, right? I think it's going to take a little bit of time, and I agree with him. There are probably other maps that work, but it's not the obvious one. Just remove the symbols and the dots, and you get 3 open and 3 close. I think that one is not a well-specified map. Just another problem that, again, if we have a map, now we have 3 problems to have the same answer. This number of paths, number of putting parentheses, and order of doing multiplication of n+1 items. Let's see, what other problems can we do that have the same answer? Here's one that's surprising a little bit. Triangulate an n+2 polygon. what triangulate means is, here's my n plus 2 is what? If n is 3, n plus 2 is 5. So this will be a pentagon. Let's draw a smaller one so we... Triangulate means break the pentagon into triangles. So this is my pentagon here. And the reason it's a one-to-one map is that because every one of these things, or the parentheses, because now I can choose any one of these problems, how can I break this into triangles? This one here, so I say there's 5 ways to do that, which is of course these 5 ways. So what I have here is this one corresponds to these triangles. So breaking the triangles is put some diagonals to break it into a pentagon. Will always break into how many triangles? No matter what you do. It will always be 3. That means you need how many diagonals to break it? 2. So, but the different triangulations, here's one that's different. So let's say this is vertex A to have a reference here. And here's I have other triangulations. I can do this and this. So here's the number of ways to break a pentagon into triangles. So if I call this A, B, C, D, E, what are the triangles I break into here? A, B, C, A, C, D, and A, E, D. So any other triangulation could have a common triangle. Like here, I still have this triangle, A, B, C is the same as A, B, C, but then the other 2 triangles are not the other 2 triangles. So this is another question: in how many ways can you break a pentagon into triangles? Pentagon because it's n plus 2, but if this would be a 7 by 7 board, would be a 9-gon, triangulation. How many ways can you break into triangles? So I say this problem has the same count as the other 3 because there is a one-to-one map between how you put parentheses and how you draw the triangles. And for every way of putting these parentheses here, there is a particular way to breaking this into triangles. That's why there's the same count. In other words, when I have an open, if this is A, when I have an open close right away, that indicates the diagonal AC has been used. So when do I have open close right away? Here and here, right? Open close. When is the line AC, a diagonal, being used? Here and here, but not in the other 3. So this parenthesis is the one that says AC is the diagonal that's cutting the first triangle out. And you guys can work out how the other 4 parentheses work to determine what are the triangles here. So when I see this kind of thing, open, open, close, close, that will correspond to why do I put the diagonals this way, the cutting diagonals. So maybe you want to think of AD, it's AD. So what is the diagonal AD in here and here as far as the structure of parentheses goes? AD in here and here. Maybe last set of parentheses. Right? This is like AD here. So every time I see this last 2 parentheses isolated, that's the diagonal AD. I think this needs some work, and I'm not willing to do it right now in class. You should do it on paper. This works for hexagons, heptagons, octagons, just the same way. For every way you put parentheses, legally, there is a triangulation, break up into triangles for that set. So this is another problem that has the same count. I have one more. One more problem with this count. let me draw it here, because I need this one here. So I'm going to say rooted binary, not binary, rooted trees with root plus n vertices. So in my case, n is 3, right? In my example. So how do I draw things together? So here's the root. I say this corresponds to the 3 vertices being, this parenthesis here corresponds to the 3 vertices looking that way. Now this is a rooted tree, so the root is marked. It's not like any node can be the root. The root is the top one. How about this one? I'm going to draw this one, and then you guys draw after that. This one corresponds to this. This way of putting parentheses corresponds to that tree. You know how I got that? Open corresponds to this branch, and the fact that it's closing right away, it means it closed the whole branch. So it tells me the fact that this parenthesis has closed immediately, this branch doesn't keep going down. That's the same that happened here, right? The first branch corresponded to these 2 parentheses, and the fact that it closed right away, it means this branch has no other vertices on it. So if we follow that philosophy, what should happen here? I still get that branch, but in this case, the parenthesis doesn't close right away. So it means what? There's another vertex here, but then closes the whole branch, which means the branch is done. So now where is this other closed parenthesis, very short branch? This way, right? What should happen here? How this one? I have the root, I open that branch, and then it looks like I'm not closing the branch until the very end, right? So inside that branch, I should have this kind of structure, right, that I have here. See, this inside is that piece in here. So what should happen from here? I have what? 2 from here, right? Like that. And what should happen here? I have something like this, maybe? Right? So is this a one-to-one map? For every way of putting legal parentheses, do we get a rooted tree? Again, the root is marked. Root is not like everybody is a root. Again, how this mapping works, every time you see a branch, you go up to where this path touches the diagonal, that is the number of open and close are equal. That's the whole branch. And then you develop that branch. You know branch ends. You have to move to the other branch this way. So how many branches from the root I have here? 3. How many branches from the root I have here? From the root.
2.
This is the 2 major branches of the tree. How many branches I have here? Only 1 major branch, right? How many branches have I here?
1.
The first parenthesis closes at the very end, so the main branch is the only branch. There's no other main branch in here. Do we see this as a one-to-one map? Do you think you can draw it for, if I say n equal 4? There'll be a lot more parentheses, right? Let's just do 1 out of curiosity. So for n equal 4, there are more options, not just 5. Let's say I can have open, open, close, close, open, close, open, close. What tree would that be? How many total branches from the root are here?
3.
So from the root, I gotta get 3 branches. Those last 2 are empty, and then this one is
1.
like that, right? I think it's quite easy to see that every legal set of parentheses corresponds to a rooted tree with the root being marked. Because if it's not marked, I could consider any one of those nodes a root, and then I get a different tree. The root has to be marked. So it's a rooted tree. Hands up, who's with me? Ah, now we're doing very good. So we have so far 5 or 6 problems, but we don't know how to solve it. I mean, we don't know the count of this thing. We know any one problem we solve, we get it done because they have the same count. But we don't know what is that count. This one?
Yeah.
Yeah.
Yeah. Because you
One?
end up with 5 as your end with the current number.
It should be like this?
It's the root plus end.
I think that's true. So this has to be root plus 4 vertices, not root plus. Okay, very good. So how do we solve this problem? There are many Catalan proofs problem, and some of them require recurrences, which is if Cn is this number, the number of ways to do that out, the number of paths legal, I'm going to call it Cn. There is a recurrence, how Cn depends on Cn minus 1, how Cn plus 1 depends on Cn. I don't want to do that right now because we didn't study recurrences yet. And recurrences is something that most of you have not seen properly in high school. Properly, I mean, usually high school teachers don't understand recurrences. This is a standard statement for everywhere in the world. It's not related to United States. It's one of the things that apparently high school math teachers don't get right. So let's pretend we didn't hear the recurrences. Let's wait for me to teach you recurrences. Maybe I get them better than the high school teachers. And then after that, we get back to this problem with recurrences. For now, we don't do recurrences. For now, we want to count those legal paths. So the problem we're going to solve is this one. And the idea is very ingenious. Like, it took 150 years for somebody to come up with this simple idea to solve this problem, because before this guy, all the proofs were very difficult. So here's the proof. Here's the answer. We're going to say how many total paths we have. I think we already said that. This is 2n choose n. That's all the paths. And this is the legal ones. We don't know how many there are. That's the ones that are legal down. Legal down. They don't cross the diagonal up. And of course, that's plus who? The illegal ones. So to be illegal, what the path needs to do? It has to cross the diagonal up. So path crosses diagonal up. So like we did so many times already, instead of counting the legal ones, we're going to count the illegal ones. So, and then we have to subtract them from the total number, right? Now we've seen this already many times. You have a question?
If you ask how many ways are there to get to those like order points?
What?
So there's like 7 order points, like one above the diagonal.
Yeah.
And if you just check how many ways there are to get to those, and then how many of you have.
I don't know, you have an answer? We try to get an answer and see. There are many ways to count these, but all ways are sophisticated, far more sophisticated than you're going to have in a homework, for example. But we've seen this idea. We want to count the legal possibilities. We count all of them and then subtract the illegal ones, right? So in fact, we count these ones here. So here's an ingenious idea for how to count the illegal paths. I'm going to draw the board again. Maybe not that big. Let's say it's a 6x6 board. So what is an illegal path? How do I know a path is illegal? I have the diagonal. This is the diagonal. Every path that's crossing this diagonal, it's illegal, right? So let's draw an illegal path. Start from here. Again, I'm counting illegal paths. Plan B, figure out this as a difference. Again, what's a legal path? It can go legal. This is legal. This is legal. This is still legal. At some point, it has to go into the illegal territory, right? Because that's what makes it illegal. So let's suppose it goes there. So here's my path in the illegal territory. That would be a valid path. I mean, it gets from 0 to n, and then being 6, 6 in here. So it's a path, but it's clearly illegally crosses the diagonal. Okay? So now, what I'm going to do is to modify this path, the illegal one, meaning get a mapping to another path from it. What I'm going to do, I'm going to say, where's this guy crossing for the first time? So the first time was clearly this, right? We're going to mark this point P, and we say this is the first illegal cross. It's possible that this crosses multiple times. An illegal path can be illegal, then back legal, then cross again to illegal, so on and so forth, right? That's possible, but we're only looking at the first illegal cross. And what we're going to do from here is reverse the path. So what happens, I'm going to keep this point P, and then for every move up, I draw to the right, and from every move right, I go up. So what is the first move that the path makes? Goes up. So where do I go if I reverse it? Right, then up, because it goes right here, right? And then right, because it goes up, right? And then, is that up? Here? Because for every move that this goes to the right, this one, the mirrored one, if you like, goes up. And from here? Up. And from here? Where do I go? I have to go up. Because this path, it follows the original path up to the first illegal cross. There has to be another one touching the diagonal. That's still legal when you touch the diagonal. The illegal one is when you're definitely on the other side. And since there, it does exactly the opposite. Wherever the one this up, this one goes right. Whenever this one goes right, this one goes up. Did you draw it correct? Up, up. Up is this right, then right is this up, then up, up, up is right, right, right. I say, I know where this one's going to end up. For sure. I don't know exactly the illegal path, but if this was the first point where it crossed the diagonal, I know what this red point is going to be. How does it look, a point that crosses the diagonal the first time? If this in here is K, we don't know where it is. What has to be the y-axis? Because this is the first cross into the illegal territory. This is K. What is this?
K plus 1.
K plus 1. So this P has coordinates K, K plus 1. It means how many remaining moves to the right P does, the original path. So remain to the right moves. If I already made K, how many moves to the right this guy has to make to N? N minus K. So remainder moves to the right. How about remainders moves up? If already it's at K plus 1, how many more up moves he must make? I don't know where, but he has to go up that many times. It's already here, so how many moves he has to make up? N minus K minus 1 like this. Now this is the part that I reversed, right? After P, so this is after P. So when I reverse it, every move that went right, now it went up, right? Every move that here went right, when I reverse it, I have N minus K moves up, and these moves are now to the right. I have N minus K minus 1 moves to the right. So I know where this red path is going to end. Because up to P is the same. And then it makes right moves N minus K minus 1. Those are the moves that this other one, the original, made up. And it makes up moves. These are the moves that the original path made to the right. So where is this point? Up to P, I had K to the right, right? Plus, how many things I go to the right? N minus k minus 1. This is to the right. This is up to p. And then he had k plus 1 up. And then the remaining up moves are n plus k right here. This is total the moves up. So where is this going to end up? The final coordinates to the right and up. How much is this? K plus n minus k minus 1.
Minus 1.
This is always n minus 1 right here. And what is this? If I add up these things, k plus 1 plus n minus k. N plus 1. This is n plus 1. Again, if I apply this strategy, take an illegal path, see where does it cross the first time? In point P. After P, reverse the path. Everything up goes right, everything right goes up. I'm guaranteed to end up, instead of NN, I'm guaranteed to end up in here. Because P was k, k plus 1 for some k. When I reverse the path, I end up in NN plus 1. Who's with me? Hands up. Very good. I have one more to say about this. Not just it ends up in here for sure. Every illegal path P, if we do a one-to-one correspondence to this, call this P prime. This is the path up to here modified. These are all the paths that end up here. Every path that ends up here, not just the legal ones, every single path from here to here, it's actually an illegal path reversed. We only prove half of this, right? We say if you take an illegal path and you modify it, you end up with a path that ends up in this place. So let's write that down. If we take an illegal path, right? The illegal path was from 0, 0 to NN, but illegal means P has coordinates k and k plus 1 is the first illegal point. That's what it means to be illegal. There's got to be a first cross. And then what did we do? We applied this mirror transformation. Let's call it mirror. Mirror after P. What we did, we reversed the path after P. And we've got what? We've got here a path that was going from 0, 0 to where? Exactly. The first coordinate is the horizontal one. To where? N minus 1, n plus 1. We agree that's what we've done. We say if you take a path that's illegal and you reverse it, you obtain a path from 0 to here. I say that's actually true the other way, too. Any path from 0 to here, it can be reversed somehow to give you an illegal path. So I think this way is the easy way to see it. I think it's a little harder to see it that way. How can we apply this procedure backward to say, here's a path, any path that goes from here to here, right? Any path. Again, I could go up, right, up, and get up here, right? Any path that's from 0 to this point here. This is the n minus 1, n plus 1 point. There's actually a reverse path to it that would be an illegal one in the original problem. How do I know when to reverse this path, the red one, back to get an illegal path?
Wherever the new illegal path crosses a k plus 1 point.
Right. So there is a point. Why does it have to cross? This red one, if it ends up here, it's guaranteed at some point it crosses the diagonal, right? Because this point is above the diagonal. So it has to cross. Whenever it crosses the first time, if I reverse the path backwards, so I take all the right moves, put them up, and all the up moves, put them right, I get an illegal path in the original problem. Why is illegal? Because I keep the point where it was crossing into illegal territory. And why is a path in the original problem? It's easy to see the same way. If this one ends in n minus 1, n plus 1, after the reverse, the reverse one will end up back to NN. Everybody's so silent. Yes.
Well, what if it crosses 2 k plus 1 plus?
I have to take the first one. I always take the first cross into the illegal territory. So I claim this is a one-to-one map. It's not just every illegal path corresponds to a path, a red one to that point. Every path to here corresponds to the illegal one. So that should solve our problem for sure, because we know how to count those red, right? What is red coming down to? It's how many paths, again, this is all paths, unrestricted, from 0, 0 to n minus 1, n plus 1, right? So how do we count all these paths? How many paths are from 0, 0 to this precise point? Yes?
2n choose, and then either n minus 1.
Right. The number of paths is 2, let's not say 2n. How did you get 2n?
N minus 1 plus n plus 1.
Is this, I have to make so many moves, choose n minus 1, that's it. Or n plus 1, it's the same thing. So I know how to count those mirror paths because it's all paths from 0 to there. So back to my problem here. If I know how to count those illegal ones, what should be, then I get 2n, choose n, is the number I want, the legal path, which I still don't know. Legal paths. Plus, you're saying that's 2n, choose n minus 1? Okay. So then the legal paths are 2n choose n minus 2n choose n minus 1. There. Right? Just the difference between the total ones and the. So I could further examine this as 2n choose n, and this is. So I can write it down in factorials if I want to. 2n factorial, it's n factorial, n factorial. This is 2n factorial, n minus 1 factorial, n plus 1 factorial. If you do the calculations, we get 1 over n plus 1, 2n choose n. That's a very simple calculation. So why I'm putting it this way? I mean, this formula is totally fine, but why I'm putting it this way? Remember when we said this is the total, right? We were asking what percentage of the total paths are legal. And I said maybe half, and somebody said, no, it can't be half. Now we know the answer. Out of the total number, how many are legal as a proportion? If n is 10. 1/11 or 9%. And if n is 100, 1 over 101 paths out of the total are legal paths. So much smaller than a half. This is the last items I have for combinatorics. And this is a little bit complicated proof that is going to take some time to digest. We don't have homeworks for it, but in mathematics, Catalan numbers are of critical importance for number theory, geometry, counting. Like I said, there are 300 problems that relate to Catalan numbers. Pascal triangle has many properties related to the Catalan numbers. We're going to come back to them for a little bit when we study recurrences, because there's a natural recurrence that you already seen in here. The subtree, it's got to be some subsequence of parentheses. So based on that, we can create a recurrence between those values and solve that recurrence to get to the formula. Now that being said, we have to go back to the mortal realm, so to speak, and to study binary counts, right? How computers add up numbers. Let's see. That's what the regular section will do in 100 minutes. We're going to do it in 15, okay? Right. Because it's just how to add up numbers. I mean, how can you be in an honor section if you don't know how to add two numbers? Right? You got to be able to add numbers. In fact, I'm sure you can add that numbers. I have no doubt already. Maybe we can do it done in 10 minutes. Beat the traffic. So binary numbers, I'm moving away from Catalan, is one of the things I like the most in this class, these Catalan lectures. Too bad we can't spend 3 lectures on it. But binary numbers are no different than decimal numbers. They have the same value, just written differently. So here's an example. 8792 in decimal. We all know it's 8 times the thousandth, right? Thousandth is 10 to the 3. Plus 7 times the hundredth, plus 9 times the tens, plus 2 times the units. So this is thousands, hundreds, tens, and units, or ones. This isn't decimal, it's in base 10. Right, that makes total sense intuitively. These are the digits, right? This is the digit values, 8, 7, 9, 2. So the way you actually can read this number is to say, how many thousands I have there? 8. How many tens I have? 9. How many hundreds I have? 7. And then you put it together in one compact representation. Every number can be, this is a unique breakout into digit sum, digit I times 10 at the power I, for I equal from 0 to something. You cannot write this number in this form, 10 at the power times something plus 10 at the power times something plus 10 at the power plus something. In any other way, if the condition is that the digits have to be, the values have to be between what and what? 0 to 9. If the digit values are constrained to be from 0 to 9, 9, where is 9 coming from? Is the base minus 1. This is unique. Every time you want to break a number into powers of 10 with digits, if the digits are 0 to 9, his breakout must be your breakout, must be your breakout, must be my breakout. Because there's only one breakout. There's no way to break it differently into powers of 10. Unless you have digits that can go more than 10 or negative values. But if the digits are 0 to 9 integers, that's the only one way to do it. This is a fundamental theorem of numbers. The break up into a base is unique. Any base. Now, keeping that value in place, we can take this number and break it up in other bases if we want to. I don't want to take that number, but we can take another number if you want. Let's see here. Let's take the number 41, because I don't want to deal with thousands. How do I break up into powers of 10? 4 times 10 plus 1. How do I break 41 into powers of 8? I want base 8. I pick a random base here. The base is going to be 8 times what plus what? Yes. How much?
5.
5 plus 1 times 8 to the 0, right? So the digits in base 8, if I want base 8, the digits will be between 0 and 7. How about 41 breaking base 4? So that's base 8. So I'm breaking base 4. What power I need? Is it 4? 4 to the 3 is how much? 64 is too big, doesn't fit. So how about 4 to the 2? How many 4 to the 2s can I put into 41? 2 plus what's remaining? How many 4s are remaining there? That's 4 to the 1. 2 again. So how much I got so far? Value, I got 40, right? Plus 1 times 4 to the 0. So what are the digits here? These are the digits. Now in base 4, the digits have to be between what and what? 0 to?
33.
How about in base 2? In base 2, the digits are what? Digits are between 1 and 0, which means I don't have to put them really. If it's 0, I skip that, and if it's 1, I put it. But I'm going to put the ones just to see it. 1 times what power of 2 can I fit in there?
5.
5. What other power I can fit? 2 to the 3
Third, yeah.
plus 1 times 2 to the 0. So what powers am I missing here? The digit for 2 to the 4 is effectively 0, right? Because I don't have a 2 to the 4, so that digit is 0. And I also missing 2 to the 2 and 2 to the 1. So how is this number going to look like if I really write it down as digits? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. What are the digits? 2 to the 0 is? 1 to the 2, 1?
0.
0?
1.
0.
And this procedure, it's easy to see you can reverse it. The way we went here and asked what power, what's the biggest power that fits in, if I give you this number, how you transform it back into decimal or any base you want. What's the value of it? So if I have to start from this number backwards, let's start from that number. Right there. 1, 0, 1, 0, 0, 1. What is this? This is in base 2, of course. What is this in base 10? How do I know which one corresponds to what power of 2? I mean, it's an obvious question. Just go from the right and increase the powers, right? So this guy is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So I can just say this is 2 to the 5 because the zeros I'm ignoring, plus 2 to the 3, plus 2 to the 0, so that is 41. The same reason this is unique in base 10, it's unique in any base. So the representation in base 2, or base 7, or base 8, or base 11 is a unique representation. So this is unique in base 2. I'm sure you knew that already. Well, how about addition, right? 41 plus 27, how much is that in base 10? Now we're going way back, right? We're not just in high school. Now we are in the 4th grade. 3rd grade, how much is this?
68.
Okay. 68. Well, suppose I want to do this in base 2. What is 41 in base 2? We already have that. 1, 0, 1, 0, 0, 1. Just like in base 10, we already arrange the bits under each other, right? Same exact thing. So what is 27? What is the biggest power that fits in 27? 4. So where is 2 to the 4 in here?
Up to 0.
0, 1, 2, 3, 4. 2 to the 4 got to be here. And then after 16, what else can I put in?
8.
8. 8 is in here, right? What else? 16 plus 8? 24. Can I fit a 4 in there? No. How about a 2?
Yes.
Is this 27? Okay. So how do you think addition is going to go in base 2? It's just like in base 10. Yes?
The digits are the same, but a 0 different from 1.
Right. So 1 plus 1. What happened in base 10 when you go over or equal with 10? What do you do? You carry it over, right? So 1 plus 1 is what? 0, and I carry a 1. Now 1 plus 0 plus 1 is? 0, carry a 1. 1 plus 0 plus 0 is?
1.
Carry a 1. 1 plus 1 plus 1? 1, carry a 1. 1 plus 0 plus 1.
0 carry 1.
And now I get the 0 and the 1. Is that true?
Carry an extra 1.
I did it wrong? I carried the wrong one here, right?
Yeah.
Because there's 1, okay, so I have no carry. That's a 0. Let's do it again. Sorry, I was rushed out. It's a carry 1 here.
Yeah.
So now this is a 0.
Yeah.
Carry a 1. So this is a 1, 0 now.
Yeah.
Well, let's see. This is what power? There are only 2 powers here. This is 2 to the 6, and this is 2 to the. This is to the 0, 1, 2, 2 to the 2. So this is what?
64 plus
64 plus 4, 68. No big. I mean, if you know how to add in base 10, you can do the additions in any base just the same, right? So I want to establish something today that has to do with the range, that's getting closer to computers. What are those numbers? How do they get represented for real now in computers? So suppose my n is 4 bits. I could have 6 bits or 8 bits or 12 bits. And what are the possibilities with 4 bits? How many possibilities that we know from sets? How many subsets are here? 2 to the 4 possibilities for 0, 1 sequences. So I'm going to start with 0, 0, 0, 0. What else can I have? 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, sorry. 0, 1, 0, 0, right? What else? 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, right? So who's 0, 0, 0 in decimal? I skipped something? I skipped 1. 0, 0, 1, 0, that's a 2. And this is a 3. 0, 0, 1, 1, 3, 4, 5, 6, 7. But I have other possibilities with 4 bits. Right? This is all possibilities that have the first bit 0. The other 8 possibilities have the first bit 1, 1, 1, 1. I'm going to write the same in the same order, but with 1 in the bit. So 1, 1, 1, 1. This one is 0, 1, 1, 1, right? 1, 0, 1, 1, 0, 1. What else? 1, 1, 0, 0. 1, 0, 1, 1. What else? Like that? How many I have here? 6. This is 1, 0, 0, and this is 1, 0, 0, 1. What are those numbers? Who is 1, 1, 1, 1? That's 15, right? This is
14, 13, 12, 11.
Is that 8 really? 1 is 1 to the 2 to the third, right? 15 is 2 to the 4, 3 plus 2 to the 2 plus so on and so forth, right? That is an unsigned. Meaning all the bits correspond to values and everybody has positive sign. I want you to remember this table here because it's going to be very useful when we do binary operations. I know it looks funny because it's out of order. Hey, why don't you just give me from 0 to 15? Wouldn't that be easier? I mean, myself, I got it wrong, right? I put some wrong values in here. Why complicate ourselves with 0 in the middle and 7 and then 8? Like, that doesn't make sense, right? It looks funny. That's how computers do it. And to add the negative sign would be really easy in here. Tuesday. There is a quiz next week.
have the same heads, so I'm just like destroying. I would go do my private problem in set 6. I didn't go to Mondays yesterday. Like I don't know why. And it was like a bad day to miss too, because we like actually tried to do something different. So like I'm really upset. Just my luck. I just finished though.
So like, what if you can concentrate or two? It's just more fun.
I mean, you can do that. The audio?
Yeah, the audio. And then like when you play it back, like it plays it back like with yeah. If I were you 100%, I recommend it. It's so good. So good.
I'm gonna break down